All right, so far we've been looking at equations in the plane for two variables in the form y equals f of x. Now, suppose that we have a curve that looks something like this. This is x and y. Suppose this curve comes around like this. It starts here, comes around, comes back over. And obviously I'm moving in this direction. Now, this curve is not a function the way we've come to love and adore functions. This thing fails the vertical line test absolutely miserably, right? So how do we represent something like this? I mean, what is this? I mean, this could possibly be maybe a particle motion. So this is actually representing the movement of a particle. Clearly, this is not a rectangular function. Which I alluded to by the failing the vertical line test miserably. So how do we represent this thing? And also, so one more thing I want you to note is notice how I did put these arrows on here kind of indicating the direction. This is called the orientation. And the orientation, in other words, the direction this curve is being drawn, is actually extremely important. So the way that we're able to get a curve like this on the xy plane is by taking x and defining it as some function of t and y as another function of t. So as t changes, x can change. So if I have like this quadratic, you know, if I just use y equals x squared, then I get this type of action or maybe this type of action. So now I've got x being able to go up and down, which means x goes back and forth. Likewise, y, I can make y move up and down as I want to, maybe a linear fashion or some type of sine wave or whatever. But now I have independent movement of x and y. I can make x go back and forth, or y is going up and down. You know, I can get all kinds of configuration of curves now. So let's just take a look at this. And what I'm going to do is I'm going to write down t, x, and y. So we're going to take values of t, values of x, and values of y. In other words, the values of t that I'm going to choose are going to define what x and y are. So I'm going from -2 to 2. So I'm going to make this -2, -1, 0, 1, and 2. And that will give me for x, see, 12, 3, 0, 3, 12, and y is going to be -4, -2, 0, 2, and 4. All I did is take x of -2, so that's 3 times the -2 squared. -2 squared is 4, 3 times 4 is 12. And all I did is evaluated x and y for these different values of t. So now that I have those, let's go ahead and take a look at what the curve is going to look like. See, I'm going out as far as 12, so let's say 2, 4, 6, 8, 10, 12, 14. Y goes plus or minus 4, so see, -2, -4, -6, that's plenty. There's 2, 4, 6. Of course, this is x and y. When t is -2, x is 12, so I'm over here, and y is -4, so I'm right about there. When t is -1, x is 3, 3 is going to be about here, and y is -2, so about there. And obviously I'm moving in this direction, so if I connect these, I'm going to put a little arrow in here that indicates the direction that I'm moving. When I'm at 0, when t is 0, I'm at the origin, 0, 0. When t is 1, x is back at 3, and y is at +2, so I'm up here. Obviously, I'm still moving in that direction. And when t is 2, x is 12, and y is back at 4. So I'm about there. So that's what my curve is going to look like. It's going to start here, come around, back up, and right there. Basically, it looks like a parabola. Okay? So let's go ahead and take a look at that quickly. I'm going to put it on the TI-84 emulator. Now, just a couple things real quick. If I go to, was it Format? No, Mode. Mode, I move down, and the calculator's probably set up function because we've been dealing with functions. All I'm going to do is move over to PAR for parametric and select it. So now my calculator is set for parametric functions. And then when I go to y equals, I now get x and y, because I have a function for x and a function for y. So I just put in this function that we're working with. Now if I graph this, you can see I started here and coming around, and it's going to stop right up in here. So there's my parametric function. Now, let's take a look at, well, let's see what's next here. All right, let's do a definition here. Let x equal f of t and y equals g of t, where f and g are two functions whose domain is on some interval I. Let's make sure you know that's an I. The collection of points defined as f of t, g of t is called a plane curve. So remember, this is my x, which is defined by some function of t, and this is what I'm thinking of as y, which is defined as yet another function of t. The equations x equals f of t and y equals g of t, where t is in that interval, are called the parametric equations of the curve. And t is called the parameter. So very commonly we take a curve and say parameterize it, which means convert this thing from maybe rectangular coordinates to a parametric function. Let's take a look at another example. I want to plot the parametric equation x equals 3 times t to the 2/3 and y equals 2 times the cube root of t. And I want to actually compare this with this previous function that I just did and see what it looks like. Well, I'm going to do the same thing with the table again. So I have the values here. I have t, x, and y. And I'm going to use the same thing. T equals -2, t equals -1, 0, 1, and 2. I'm going to keep this on -2 less than or equal to t less than or equal to 2. And when t is -2, I'm going to have 3 times the cube root of -2 squared, squared. That's actually approximately 4.76. I need that approximation so I can actually put it on the curve. And y is going to be a negative, well, we're roughly approximately -2.52. And that's the 2 times the cube root of -2. See, at -1, x is going to be equal to 3. Y is going to be equal to -2. At 0, I'm going to have 0, 0. At 1, I'm going to be back at 3, but a +2. And then at 2, I'm going to have 3 times the cube root of 2, which is approximately 4.76. Oops, this is a negative. No, that's not. That's positive. And for y, I'm going to have 2 times the cube root of 2, which is approximately 2.52. So I'm going to make my curve, or my axes here. Let's see, x is going no bigger than about 5. So if I go 1, 2, 3, 4, 5. Y is going 2.52, no bigger than about 3 in each direction. 1, 2, 3. -1, -2, negative 3. My first coordinate, x is at 4.76, which is like right in here someplace. And y is negative 2.5-ish, so I'm down in here somewhere. My next one, x is going to be at 3, and y is at negative 2. I'm coming this way. Then I'm at 0, 0. So I'm continuing like this. And then I'm back at x equals 3 and y equals positive 2. So I'm here. And then I'm at x equals 4.76, the same place on x, and then 2.52, so I'm roughly in here. Okay, granted this is not exactly to scale, but you get the general idea. So that's what it looks like. It looks an awful lot like the function that we just graphed. Now, let's take a look back at the calculator. Go back to y equals, and I'm going to make an adjustment here on my calculator. I'm going to make the first one just a straight line. And then this one, I'm going to make that circle so we can see it moving along. And turn it on. See, I have both of these functions in there. Now let's graph it. There's the first one. Here's the second one come along. See, the second one started here, roughly. And there she is. She stopped up here. So basically, it's the same curve. It just doesn't extend out as far. So the conclusion here is that parametric curves are not unique. I can find more than one set of parametric functions to represent the same curve.